Light is considered to be an electromagnetic wave. Prior to the 19th century, there were two prevalent theories on light. Sir Isaac Newton believed that light was a stream of particles that came from a light source and entered the eye. He used a prism to refract white light and show its components. His theory was widely accepted due to his prestige and his reputation in physics already. However, this theory didn't explain diffraction, interference, nor did it explain polarization. There was another scientist named Huygens who had this theory of light. His theory wasn't as accepted, however, it explained some of Newton's missing points. Huygens' wave theory stated that every point on a wavefront may be considered a source of secondary spherical wavelengths which spread out in a forward direction at the speed of light. The new wavefront is tangential surface to all of these secondary wavelets. This means that every point on a wavefront acts as a secondary source and creates and produces secondary wavelets that are the same speed as the original wave. Huygens' theory was further proved in 1801 by Thomas Young's theory of light, using sunlight that was diffracted through a small slit that was used as a source of illumination. He projected the light rays from the slit onto another screen containing two slits placed side by side. The light passing through the slits was then allowed to fall on a screen. He observed that when the slits were large and spaced far apart, and then in close to the screen, the two overlapping patches of light formed on the screen. However, when he reduced the size of the slits and brought them close together, the light passing through the slits and onto the screen produced distinct bands of color separated by dark regions in a certain order. In 1865, Maxwell derived an electromagnetic wave equation with velocity for light, and it was in close agreement with measurements made by his other experiments, and deduced that light is an electromagnetic wave. In 1888, Heinrich Hertz produced electromagnetic waves in a laboratory and measured their wavelength and velocity, further proving Maxwell's prediction that light was a source of electromagnetic waves.
I'm going to talk about single slit diffraction. The slit that just has one hole and rays comes out of this. So you may think that if there's one slit, there wouldn't be any wave interference. But it's like, we punching on the hole in the area in our car. It is a small slit, but comparing with the double slit, is a lot bigger than that. We can pretend to divide our slit into two pieces and compare the path length of the light coming from these two pieces and discover what sort of interference pattern we will get when they interact. So now we start with the slit that hit to the middle of the wall, and let's choose the point at the two edge of the slit, so they're gonna have the two equal distances from the center of the slit. So in this case, the path length to the center point on the wall gonna be the same. So if from that we know that they will interference constructively, so with each other. If we choose these 2 points farther from each other, but they're still in the same distance from the center of the slit, we will have still the same equal length to the center of the point of the wall. So in this case, the two rays gonna have the constructive interference as well. So we're gonna see a lot of constructive interference going on when the distance between the center and the edge of the points are the same for both rays. So now imagine that we want to find a spot on the wall, the darkest spot. So we have to find the places that are the most destructive interference happens. So instead of taking the points symmetrically across the slit, let's take 2 points, one on the top of the edge and one just below the center of the center. So and then compare these two together. So because all the pairs are in the same distance apart from the slit, so we want to measure the path length from each pair to the same spot on the wall. Each pair will have the same difference in path lengths. So if you find the point on the wall where one pair has the half wavelength difference in the path length, then we have found the pair points where all the pairs are they're gonna be there. So in this case, there will be a lot of destructive interference at that point from all of the different pairs. So we'll see an overall dark spot in that area. So now at the end we want to compare the single slit with the double slit interference to see how they look like when they're on the wall. So in the particular we're gonna have the center bright spot, which is larger than we're gonna have in the double slit. We can view the diffraction as light spread out when it comes up to the hole or other barrier, and because they're trying to get out of that barrier. In the process of spreading out, it interferes with each other, and the darkest spot will be created.